One of the first videos we did for this channel was about the Futurama theorem, which is a pretty amazing thing. It's about mind-switching mathematics, and a real theorem that appears in one of the Futurama episodes. And well, I was going strong when we were recording this episode, and we were already at, I don't know what it was, 25 minutes. So Giuseppe told me, you have to stop now, you have to stop now. And well, I stopped then. But the video actually became quite popular. And so I thought, well, why not do a part 2 where we talk about all the stuff that I didn't get around to talking about last time. Okay, so that's what I'll do today. So when you think about the Futurama theorem, you'll actually notice, well, it's a lot of fun, but mathematically speaking, it's actually pretty, well, not very interesting. So outside Futurama, no applications, I think. On the other hand, that stuff that I didn't talk about, that gets you into territory that's extremely important within mathematics. In fact, into some sort of incarnation of yin and yang within mathematics. It's called the parity of a permutation, of a parity of a mess. And it's something like odd and even, or left-handed and right-handed for permutations, for messes, for shuffles. Whenever you rearrange something, it's there somewhere in the background. And like within mathematics, it's very, very important. And Rubik's Cubers, for example, they know about it, and a couple of other people. Anyway, so let me talk about this stuff. So quick recap of what has been happening so far. So I'll stick with the Futurama setup, because most people will be familiar with this. So there's the professor, and there's Amy, and the professor's just invented this mind-switching chair. So you sit on the chair, both characters sit on the chair, you push the button, and minds get switched. And the way I've set it up is like this. So here we've got always two diagrams. One stands for the body, and one stands for the mind. That's the body. The one with the triangle is the mind, okay? So they sit on the chair, they push the button, and minds get switched, okay? Now this chair comes with a little bit of a flaw. It's a great invention, but once two bodies have sat on the chair and switched minds, if you try this again with the same two bodies, it's not going to work, okay? So these two guys at the moment, they're stuck, right? You know, they can sit on the chair again, push the button, but minds won't get switched. So their idea is to just bring in a couple of their friends and then use their bodies as temporary storage and kind of swap minds around and hopefully eventually get everybody sorted out. So they do that. So they get in like 9 characters in total, well, 7. So 7 plus the 2 that were there before, that's 9. And it's the usual crowd plus a couple of additions for that episode. And then they go for it, right? And, well, they don't get anywhere really. Well, they just get into a big, huge mess. And that's the mess there, okay? That's the mess. And in fact, the only way out is to bring in outside help. Outside help comes in the form of the Harlem Globetrotters of the future. There's these basketball players there who also happen to be extremely good at maths. And they come up with this theorem that you see there in the background. And the theorem allows to sort out any mess whatsoever, and you don't even have to know how it came about, right? And you can do it. So it's something very, very neat. And not only do they come up with the theorem, they also help sorting out the mess. And that's basically where I'll pick up the story, and we'll just have a look at the clip again where things get sorted out. It's not clear that they actually get sorted out, but they do, and it's all correct. What I want to do is I want to count the number of switches it takes to sort out this mess, okay? So in the clip, there's always going to be 2 switches happening at the same time. So the way I'm going to count is 2, 4, 6, 8, and so on, okay, until we're finished. Okay, so here we go. 2, 4 switches, 6 switches, 8 switches, 10 switches, 12 switches, and one more, 13 switches, okay? So we've got 13 switches. The theorem sorts out this mess in 13 switches. Okay, well, I mean, the theorem just does everything, you know, any sort of mess, but what it doesn't do, it doesn't try to be, you know, particularly efficient. And actually, if you have a really, really close look at how this mess comes about, then you'll notice that you can actually do with less switches if you're just really smart about it. You can actually do the whole thing with 9 switches. Okay, 9 switches. Can you do even better? You know, I mean, that's something that you kind of ask in mathematics quite a bit. what's the best way of doing it? What's the least number of ways of accomplishing something? It's a kind of a theme that runs through mathematics. And well, just in general, everybody's interested in doing things the best way possible. Okay, so let's ask, can we do any better? Well, actually, it turns out with this particular sort of chair and the setup we have here, we can't do better than 9. If you want to do better than 9, what you actually have to do is you have to ask the professor to go away and fix his chair. So that's what he's actually going to do in a second. So he's going away and he's fixing his chair. And he comes back with an improved chair, okay? And an improved chair actually doesn't have any restrictions anymore, right? So you can put like Amy and the professor on and push the button 500,000 times and the minds are going to get switched 500,000 times, okay? All right. And now we're going to just try and do better than 9, okay? Let's see how well we can get. And well, we make a mistake. We put Fry in charge, okay? So if we put Fry in charge and he just gives commands, use which was that guy and use which was that guy, and let's just see how he goes, right? So he goes for it and eventually he actually manages to sort out the mess. It takes him, well, 65 times. That's not an improvement, right? Then maybe he goes again and again and again and again. And let's just note down everything he does, right? Okay, so here we go. That's what he does, right? So he does like 35 times to sort it out, then 21, 15, 79, all this sort of stuff. Now, actually, I haven't shown this to Giuseppe, so I'm going to ask him. What do all these numbers have in common?
They're odd.
They're odd. That's exactly right. They're all odd. So they're all odd. They're all odd numbers. And in fact, that gets us to this yin and yang thing, okay? So it turns out that this mess here, when you sort it out with just using swaps, well, you can do it in many, many different ways. But whatever you try, you're always going to take an odd number of swaps. It's not possible to sort this thing out with an even number of swaps. Absolutely not possible. And so that makes this thing here, what mathematicians say, an odd permutation or an odd mess. All right. And well, that's kind of true in general. So whenever you look at some sort of rearranging of things or some sort of, bringing things back into a certain order, that's going to be in the background. So for example, I've got these animals sitting here. If we want to arrange them so that the smallest one is here and the next smallest one is here and so on, you'll actually turn out that no matter what you try, there's many, many different ways of doing this, it will always take an even number of swaps. So that's an even mess or an even permutation. And it becomes really important for puzzles like this, for example. When you've got this sort of information, it actually turns out that all the messes, the shuffles of a Rubik's Cube, when you really, really have a look at it, they're all even permutations. So for example, this is an even permutation. You kind of give it a couple more twists, even permutation, even mess, even shuffle, whatever you want to call it, right? So this is something very, very fundamental, right? So there's the even permutations, there's the odd permutations. And again, even permutation or odd mess or even mess means if you want to sort this out with swaps, it's always going to take an even number of swaps. Odd mess always takes an odd number of swaps. Okay, so what I want to actually show you, and my colleagues in the maths department have advised me against it because they think it can't be explained to a lay audience or people who are not specializing in mathematics, is why this is the case. And also, what's the least number of swaps that we need to actually sort out this particular mess or any mess. Okay, so here we go. Now, let's just put somebody in charge instead of Fry. Let's put somebody in charge who's actually smart. Who's smart in Futurama? Well, Professor definitely. Leela is also pretty smart. So let's put Leela in charge. Let's have a look at this. Actually, I'm going to pick on Giuseppe again. Okay, so if you've got this mess and you want to sort it out, right? I mean, what does everybody really do, right? So if you want to, if you want to put this thing here in order, what do? You probably focus on Bender, right? And then how do you get Bender sorted out?
Well, I would put him with the guy that has his mind.
Yeah.
So with the emperor.
With the emperor, that's right. And then?
So I would pair them up pretty much.
Yeah, you pair them up and you swap, right?
Yeah.
So that's what pretty much anybody would do, I think. And then, well, we would try to maybe sort out Fry. What do we do?
Zoidberg.
Yeah, so Fry with Zoidberg, you just pair them up and you go. And I actually keep count of how many swaps it takes, okay? And then lila with, well, there's the lila mind, right? So, and you just keep on going like this, right? And sort it. And I call this maybe the straightforward approach or something, right? This is a straightforward approach. Takes 7 swaps. Better than 9, right? Better than 9. So the improved machine really made a difference. But now the question is, can we do even better than this? Right? Can we do even better? Well, I mean, one thing which is good is it's also an odd number, just like what I said. Right? It's an odd number. Okay. Now, to get to the bottom of this, I've got something really cute set up here. So I'm really proud of this. And it actually, it's the same sort of setup that we use for the Futurama theorem. It actually works very well for this one here. Okay, so here's our 9 characters. To be able to actually describe what's happening, like really describe, I need a bigger mess than what we have here, okay? So I'm actually going to bring in a few more characters here. So it's, for example, Nimoy is down there, Spock, and I'm going to jumble them up, okay? So that's a mess now. And now I'm going to first find the underlying structure of a mess, right? There's always some order in a mess. And I want to just show you what that is, okay? Now the people who've watched the Futurama theorem clip, they know what it is. Everybody else, here we go. So we'll focus on one of those guys here. At the moment there's Bender and there's Lila's mind, so let's just have a look at where's Lila's body, right? So we will just make an arrow here. Then here's Kif's mind, Kif's body is over there, so we make an arrow. There's Fry's mind, Fry's body is here, an arrow, and we just keep on going like this, okay? And obviously, there's only a couple of places where these arrows can go, so eventually we have to come back to the beginning, right? And, we actually do, right? So after 6, it's basically 6 times we have to draw an arrow here, we got back to the beginning. Now, we didn't pick up those guys, so we just start again with this one here, and we go here, 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 here. Again, another cycle, so in mathematics this is called a cycle. And then, well, we're not finished yet, so we do this one here, that gives us a mini cycle. And then there's actually one guy who, there's nothing happening here, but we're still always connecting mind to body, so if we connect mind to body, we have to go like this, right? Okay, now we can sort out this thing. I like just graphically make it look a little bit nicer. So here we go. So what I've done now is I've just really made these cycles looking cyclical, right? So that the minds are always next to the body. So mind next to the body, mind next to the body, and so on, right? And so what we've got here is called a 6 cycle because it's got 6 guys in it. That's a 2 cycle. That's a 5 cycle. And Giuseppe, what do you think? What is this?
1 cycle.
That's a 1 cycle, that's right. So it's a 1 cycle. Okay. And now the key to really understanding what's going on here is to have a look at what happens when we swap 2 minds. Okay? And there's actually 2 possibilities here. Either the 2 minds are in like 2 different cycles, or they're in the same cycle. Okay? So let's just see what happens if we swap those 2 minds. Okay? Ready for the magic? Oh, he's ready. Okay, so we swap these 2 minds, and what happens is
we get a bigger cycle.
We get a bigger cycle. That's right. So the 2 cycles merge. So I call this sort of thing an outer swap. Okay, an outer swap. So an outer swap. So the 2 cycles merge, and in terms of numbers, what it means is that the number of cycles goes down by 1. Okay, so before we had 4, and since these 2 merge together, we now have 3. 1, 2, 3. Okay. Okay, let's just do another example here. Here. So let's make the swap. Right, make the swap, and what do we get? 1 big cycle. Right? So number of cycles has gone down by 1. And actually, when we kind of go backwards here, just going backwards, you see that's already one of those other swaps where we have 2 guys inside a cycle. When we swap those, the cycle actually splits up into 2 parts. Okay, so let's just do this. So the cycle just split up into 2. Another example here. Let's just go for a swap in here. We do that. The cycle splits up. And so the effect here is that the number of cycles goes up by 1, right? But the main thing here to remember is that no matter what we do, the number of cycles either goes up by 1 or it goes down by 1. It's very simple. Yeah?
It could stay the same if they're within the same cycle.
No, if they're in the same cycle, like what we just did here, it always splits up. It always splits up into, so nothing stays the same. So as soon as you make a swap, the cycles either split up or they get merged. and the number of cycles either goes up by 1 or goes down by 1, depending on whether you make an outer switch or an inner switch. Okay, so that's the key to everything. So let's just have a look. Okay, so we start out with 4 cycles, okay? And where do we want to go? We want to sort everybody out, huh? So we want this. And what is this? Well, it's 14 characters, and it's basically 14 one cycles, okay? So 14 one cycles. Okay, now we want to do this with swaps, right? Well, one swap, well, we have to get from 4 to 14 somehow. Well, obviously what we really want to do is we want to kind of go 5, 6, 7, right? We don't want to go the other direction. We definitely don't want to go backwards. So we're going to go 5, 6, 7, 8, 9, 10, and so on. So it's a difference of 10, right? So we should be able to get there in 10 steps. Now, are we going to split cycles, or are we going to merge cycles for this?
We're going to split cycles.
We're going to split cycles, right? Because we kind of really want to kind of break them down basically into these individual components, right? So every single thing we do here is going to be just go inside swap, 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 swap. And I just want to show you how that works with 10 switches. Here we go. So for example, we take those 2 mines there, swap, and that breaks up this 2 cycle. And actually it turns out that to break up one of those cycles into individual components, you just need 1 less swaps than guys in here. So for this one we just needed 1. That was a 2 cycle, we needed 1. For this one we're going to take 4, and for that one's going to take 5. So 5 swaps plus 4 swaps plus 1 is 10. Okay, so let's just do it, right? So let's break up this one here. So I'll just do it, right? And I actually always take mines in kind of adjacent. It doesn't really matter what you do, it's always going to break up the whole thing. But this is kind of neat when you kind of take these mines in adjacent guys in here. You always kind of isolate one out like that, right? And there's the counter of cycles. Right? So at the moment we're at 13 cycles, and we just do one more step like this. That gets us up to 14, all right? Okay, and now when you kind of have a look at this, it's pretty obvious that we can definitely not do better than 10, right? And 10 does it. So 10 is the minimum number of swaps you'll need to break up that mess, okay? So blatantly obvious? Yeah, obvious, right? Okay, so now we can go back to our mess that we're really interested in, the Futurama mess, okay? So what have we got here? We've got how many cycles?
2.
2. And where do we want to get to? How many guys are here? 9, right? So it's 2 and 9. So what's the minimum?
7.
7, right? 9 minus 2 is 7. So actually 7, that one that we got with the straightforward approach, was best possible. And actually, it turns out that if you do the straightforward approach, you're always going to be best possible. You know? And if you actually have understood what I've been talking about, just go back to when we did the straightforward approach and let's have a look at it, and you see, actually, yes, I'm always doing inner swaps here when I do the straightforward approach, and that's why it's got to be optimal, right?
And this is always working when the machine is upgraded, that you can do all the swaps.
Yeah, I mean, the upgrading of the machine is just a gimmick, really. I mean, usually there's no machine, you're just swapping, right? All right. Right, so that's pretty good, right? It says something. But the really deep thing is to see that, you know, this guy is an odd permutation. And it's based on the same sort of insight, you know, the breaking up the cycles and kind of going up by 1 and going down by 1. Now, I'm just going to show you for this particular mess, but if you understand why this is an odd permutation, you can do this for any permutation or any mess, right? You'll see that it's always going to take either always an odd number of swaps or always an even number of swaps. Okay, so I'll show you why this is an odd permutation, why it will always take an odd number of steps to get this sorted out. So let's put Fry in charge again. Okay, let's put Fry in charge again. So he doesn't know what's going on, right? So he's just going to make like random switches again, right? So sometimes the number of cycles is going to go up by 1 and sometimes it's going to go down by 1, okay? Cycles at the moment, we've got 2. Okay, now we make our first switch. Like Fry makes his random first switch. How many cycles are we left with? What are the possibilities? We can either go down by 1.
You can either have 1 cycle by merging both of them, or you can have 3 cycles by splitting the big
That's right, so 1 or 3, right? Okay, now he makes the second switch. Again, we don't know whether he's going up or going down. So what are the possibilities? Well, 1 cycle we can't go down, 1 cycle, that's it. But we can go up, so we can go to 2. From here we can go to 2 or to 4. So we can either go to 2 or 4. That's the only possibilities. When 3, How many cycles? What are the possibilities?
Well, you can go back to 1.
Yep.
Or you can go now to 3
Yep.
and to 5.
And to 5. And that's it. And if you just have a look at it, it's pretty obvious what's going to happen always in terms of odd and even. In the first step, it's always going to be odd, right? That's even, that's odd, and then it continues like this, right? So on the fourth one, it's going to be even, right? Yeah. Then odd, even, odd, even, odd, even, odd, even, odd, even. So it's going to be like that, no matter what Fry does, right? You know, I mean, if he did actually know what he was doing, he would be finished after 7, but he probably doesn't finish after 7. So what other numbers can he finish on, right? We want to see that it's always going to be odd. Okay, and that's actually already pretty obvious. A lot of you will have seen it already, you know? But I'll just say, okay, what are we aiming for? Well, we're aiming for 9 cycles, okay? 9 is odd, right? 9 is odd. So the only places where we have any chance of actually solving the whole thing is on the odd cycled bits, right? So the only places where we can actually sort out the thing are on 7, 9, 11, 13, 15, and so on. And that's the whole explanation, right? That's the whole explanation. So it's an odd mess. Pretty good, right? Now, I actually didn't really show you where this comes up. So we're going to do another video where we actually have a really, really neat application of this, and to the Maths Museum in Futurama. So I'll just show you the clip just to whet your appetite, right? So here we go.
So what do people do for fun here?
Do you enjoy partying all night with plenty of ale and lusty women?
I sure do.
Not us. We spend our leisure time in the Mathematics Museum.
So that's the Mathematics Museum, and you probably recognize this little puzzle there that's built in there. So this odd-even permutation business plays a big role in kind of understanding this thing. So there's going to be another video about this stuff. So just in case you made it to this point, I just actually tricked you in sitting through a whole mathematical proof. So you may have not noticed it, but I mean, in a maths book, what we've just done looks like this, right? So, you know, pretty cool, isn't it?